Hello and welcome to Watch This Space from Rivada Networks. I'm Brian Carney, and with me today is Cristian La Rocca. Cristian is a senior network engineer, and we are going to talk today about building networks in space. Cristian, welcome to the show. Thanks for coming on.
Hey Brian, thanks for having me today.
So, when we talk about at Rivada, we say we're not just building a constellation. Building a constellation is hard enough, right? But we're building an orbital network is how we sometimes refer to it. And I just wonder if you could start out by telling our viewing, listening audience what that means. How is a network in space different from, just a satellite or two up there? What are the complications? How do you think about networking in space?
Yes, well, first, creating a network in space means creating a system of interconnected nodes and links that can operate to some extent autonomously to transmit data without relying on any ground infrastructure. And this space network is like mimicking terrestrial ones, but it lives completely in orbit in space. And we use inter-satellite links, laser links, instead of cables to connect network devices. And in our case, we are building a carrier Ethernet network, and this is gateway-less. This is the difference that we have when we compare with others. And this is not the same, for example, like Starlink, that they provide internet access. So our customers, they are expecting a very strict service level agreements. They want committed throughput, the lowest possible latency from A to B, and they also expect to have a low jitter, right? So with internet services, it's not the same. You get up to one throughput and it's best effort. So what it means for us to have this in space. So we need, of course, satellites, and then each satellite is a network node. And inside each satellite, we have an advanced processing unit, and it's an onboard processing unit to enable routing decisions, right? This is like like a small brain inside each satellite making decisions. And then we also have like inter-satellite links. This is a laser between two nodes. This is a high-speed, very stable link to transfer data. And last but not least, we have also network protocols to make the network works. We have, for example, IP or MPLS. This is used for data forwarding, efficient data forwarding. And then we have dynamic routing protocols. And these dynamic routing protocols is like a piece of software we have on board. And it is used by every network device to know where the other devices are located, right? It's like following like Google Maps, something like that. And this protocol needs to adapt to failures and topology changes all the time. So long story short, we have to replicate terrestrial network in space. And the idea is compelling, but the process is not straightforward as you can imagine.
Sure. Okay. You laid a lot on me there, Cristian. So let's see if we can unpack it a little bit. So the first thing I don't know if it was the first thing you said, but the thing that kind of first thing that's stuck out at me about what you were describing is that there's a real difference between a satellite constellation where the data goes up to a satellite, comes straight back down to a terrestrial gateway, and then travels over terrestrial fiber or some other infrastructure, whether that's, it's from that gateway, it's connected to the internet, or you're trying to get back to your corporate headquarters or something, right? There's this bent pipe architecture, which I guess we can think of as traditional kind of satellite communications, where a big part of the data path is not in space at all, right? I think a lot of people think, oh, well, it's satellite, so of course it's in space. But what we're talking about in kind of previous generations of satellite communications is one in which those satellites themselves are very dependent on being able to communicate with these gateways to complete the data path and send your transmission, transfer your file, communicate in whatever way that they're doing. And so with the Rivada, with the outer net, is taking that gateway out of the picture and routing the entire data path on network, as it were, right? On our orbital network, as I called it earlier. And that means every satellite becomes a node in our network that has to know something about the topology of the entire orbital network to be able to route your traffic, right? If you're a customer from that satellite to this satellite to this satellite, and then back down to someplace else. That could be halfway around the world, right? Is that
That's That's correct. That's correct. So we need to know, for example, the location of every single node at all the times, because you have to, if you think how it works, we have the ground device that is connecting to a satellite. And as you described, the data travels in completely through space. It never touches ground. It goes like laser from A to B, and it goes down to on the remote side. And to make that happen, if you think in all the things that should be in place to make this work, traditionally you have a static network where your network devices are in a place with screws, very fixed, and you have
right?
a perfect cable. And here we have a network that is constantly moving all the time, very fast, a very high speed. And the link between these two satellites is a laser that has to be perfectly aligned all the time. So thinking everything that must be in place to make this connection happen. And this puts a lot of pressure, for example, in routing protocols. So traditionally, when you take classic routing protocols that you can find in any terrestrial router, they expect a stable network. They expect a topology that is very static with some occasional changes. They are not prepared, and they were not designed to be all the time updating the location of thousands of devices.
Right.
And this is a huge challenge for us. So we have to be very creative when we pick and mix protocols and how we adapt them to make the communication happen. This is one of the challenges. I can mention others if you want, but the routing challenge is probably the most interesting one that I have to solve.
Right. So just to dwell on that for a second, right? I've got my satellite dish. I realize it's a phased array antenna probably, so it's probably a flat panel, but we'll call it a dish. And it's talking to our satellites, and those satellites are moving overhead. They're moving north to south and south to north around the globe. So the satellite I'm talking to is going to change, and the satellite that is, at the other end of my data path is going to change over time as those satellites continue in their orbits. And the position of all the satellites in between, right? If it's doing 3 or 4 or 5 hops across planes, um, those are all changing too. And so over the course of a session, I don't know if you can tell me how often that would happen, right? But there have to be these handoffs, and it has to be rerouted, you know, with
Yeah,
some frequency, right? To make sure that my data connection remains intact the entire length of my whatever I'm doing, transferring files or having a call like this or whatever it is that I'm using the network for.
take what you said and multiply that by thousands of times. Every 5 to 10 minutes, we have to update thousands of locations all the time. And this is very interesting because if we use routing protocols as they are, we will make them crash. We will make the hardware crash because the resources also, this is another limitation. The resources we have on board are pretty limited, right? And we can't expect to have a huge compute power there. So yes, you can think of thousands of updates every 5 to 10 minutes. And yes, routing protocols are definitely not prepared for this environment.
Right. Yeah, and there's limited power, as you said, there's limited processing power, and we want to use as much as possible of that to deliver our customers data, not to be managing our own network too, right? So the routing protocols have to be efficient so that we're not sort of eating our own, I don't know what the right metaphor is, sort of, you know, burning the furniture to keep warm or something, right? We can't consume all our network resources figuring out how to route traffic because we need to save those resources for the traffic itself, right? This is part of the
Absolutely.
problem.
Absolutely. And that is why our network, we don't rely on ground infrastructure, but we need systems on the ground. We depend on them to some extent. And we have a big brain on the ground doing all the heavy calculations. And then inside each
Okay.
satellite, we will have like a smaller brain, but we need some logic. So I like to say that we have like a distributed logic with a central brain on the ground. And this is a way we have to reduce the computational power on board. And this is all new. This is nothing that you will find to buy in the market. You have to develop. So yeah, the level of innovation in that part is pretty awesome.
Yeah, no, that's super interesting. I was going to ask you why nobody's done this before, but the more we talk about it, the more obvious the answer seems. It's hard and it requires some, as you said, some real innovation. Um, are there lessons that we can take from, say, mobile terrestrial wireless networks to, because there I know the base stations, so to speak, aren't moving, but at least the handsets are. Are there things we can learn from how mobile networks handle, kind of reconfiguring networks on the fly or handovers, that kind of thing that we can apply to this, or is a
Well,
completely different set of problems?
it's completely different. We can reuse like the air interface to some extent. I mean, the wireless communication, that is, we can reuse part of it. But then when you think of mobile networks, they have all the infrastructure is static on the ground. They can create aggregation points. The location is always the same. So you take all the traffic from all the mobile users and you send the traffic to that gateway. And as we said before, we don't have any gateway. So when it comes to routing, it's completely new. And when you talk, we are in contact with a lot of vendors, the top leading vendors in networking, and
Right.
when they see the challenge and how interesting is the project, they stick with it instantly. So again, the challenge is nice to solve, but it's very complex. But yes, everything has to. We can't reuse protocols. We have to take protocols that we know and adapt them to make them work. So we can reuse very little, honestly.
Okay. No, that makes sense. Um, and I assume too that there's a capacity issue, right? One of the reasons why mobile networks, you know, offload traffic onto, we think about mobile networks as wireless, but the fact is most of that traffic gets dumped, as you said, into a gateway and then it goes over fiber. And the same is true with satellite, right? That people want to get that stuff off their network and onto somebody else's as fast as possible because they want to, free up resources for the next user or whatever. So there's a dimensioning problem, if I can put it that way, I imagine too, where we have to say, okay, we need enough power, we need enough throughput to handle keeping that traffic on net, right? We can't kind of fall back on an offloading strategy if we're trying to keep it on net. And that must have implications for, again, for power, for throughput of the intersatellite links and for the kind of the design of the whole system now.
Yeah, and the thing, the biggest problem if related to this is the service our customer are expecting, because packet loss in our environment is not accepted, and so we have to deliver a very stable service in a very unstable environment. So when you take what you mentioned before, all the constraints we have, like throughput and everything else, yes, it is a complex thing to do, and we are working. So we have to be very creative in our team to achieve this thing. So, for example, one of the milestones is we will be MEF certified, And when you want to be MEF certified, the service that you deliver has to be very good. And yes, again, satellites are not a usual environment for that.
Right. And MEF stands for Metro Ethernet Forum, is that right? And this is a.
That's correct.
Can you explain what MEF certification means, or what the MEF standards are, in case people have never heard of MEF?
Yeah, MEF is a standard for carrier or service providers, and it defines parameters that you have to have in your network to be compliant with them. So the idea is to have a standard, and you can interconnect networks from different carriers and following the same standards. And if I buy a service that is MEF certified, I can expect some level of features. And it's a way that the industry found to be all on the same page. And this is pretty usual in service providers on the ground. We are taking this to space. And there are other companies that offers carrier Ethernet services in space, but always with gateway. Ours is gateway-less.
Right. So the MEF standards are standards primarily for terrestrial networking or interconnecting of terrestrial networks that have started to be used or applied to satellite-based communications, but in the cases other than the Rivada outer net, they're getting MEF certification, but they're still using a gateway-based architecture. Is that fair to say?
That's correct, yes.
Okay, so we talked a lot about the complications and the difficulties of doing this, and but can you say a word about why we would do this? What are the advantages of achieving this when we've achieved this? Whether that's for our customers, if it's for us, what's the upside for everybody of building an orbital network instead of a gateway-based constellation?
Yes, well, the first benefit I mentioned before is that we route traffic directly in space. That is a big win. Then we can provide global coverage on demand, and this means that we can connect any point with any other point around the world, no matter where you are. And this happens in a very short amount of time. So if you have to connect, for example, London and Buenos Aires, you probably need to talk to different service providers or different players, and you have to wait weeks for that to happen. And we can do that in minutes. We can provide you that connection from Buenos Aires to London end-to-end in minutes. And
wow.
You will find, you can say, hey, Cristian, but there are service, network as a service or service provider that can offer you global connectivity in minutes, but you still have to solve the last mile problem. And we don't have that problem. We have the last mile, which is the uplink to the satellite. And then we provide the global connectivity with the satellites. And that is something that is not there. So you can provide, if you think in big cities, maybe you don't see the benefit, but I go to, for example, Argentina, go to the north and try to do this same thing. It can take months for you to get a service. That is another big win, I think. Then the latency is reduced a lot. We can provide very likely the service with the lowest latency in the market. And yeah, and also I think this, sorry, go ahead.
No, I was going to say that's at least in part because the laser communications travels faster through near vacuum in space than it does through fiber optic cable, right? So it's 33% or something faster. So even though you're traveling farther, the speed advantage of being in space allows the end-to-end latency to be lower. Is that right?
Yeah, that's correct. We move data close to the speed of light, kind of. And if you take an optical fiber, for example, the speed is around 2/3 of the speed of light. So even if you put a cable from Buenos Aires to London, our data moves faster than in a cable.
Wow, that's cool.
Yeah, that's
Um,
cool.
Now, I have a slightly cheeky question, and we're not supposed to talk about the competition, but one of the things that I hear from people sometimes is, well, lots of other companies are now adding intersatellite links to at least some of their satellites. They're putting these laser links in place. So laser links between satellites aren't that big a deal. But what I hear you saying is it's one thing to put a laser or two or three or four or six on your satellite, um, but to really build a kind of an end-to-end network in space requires a lot more than just, the laser hardware. Even assuming that your satellites are in the same shells and therefore they have, persistent line of sight with each other, that they're not at different inclinations or different altitudes and therefore flying past each other all the time. Um, that this is not a simple matter of, oh, well, we have lasers on our satellites to create this end-to-end data path in space, right?
No,
there's more to it than that.
absolutely. There's a lot more. Yes, for you need to add all the routing component, which is huge. For example, just to give you an idea of what we are doing, we are developing a predictive routing solution that is really cool. So as I said before, traditional routing protocols are more reactive. They react to changes in the topology, for example, but that is not our case. So we took cutting edge routing protocols and technologies like segment routing and EVPN. They are just named, it doesn't matter. But the thing is, we are adding a predictive component to mitigate the effects of the constant moving network. So it's not just putting laser links. You have to add a lot of a logic behind the network. And yeah, it's not as simple as putting one link between two satellites.
Right. There's software that you guys are working on to do this predictive routing. There's system architecture too, right? The fact that our satellites are in a single shell and kind of move in concert with each other allows us to maintain these persistent laser links, with just, kind of one seam, as it were, in the network, unlike, multi-shell, multi-orbit constellations that have, problems with aiming the satellite, the lasers, maintaining connections or constantly breaking them. And I know people have been working on, breaking and reestablishing those connections as fast as possible, but it still seems to me it's probably better to break them as seldom as you need to, right? It's in terms of guaranteeing throughput and guaranteeing a service level to our customers.
Yeah, absolutely, absolutely. So yes, the system that is behind is huge. As I said before, we have a huge brain on the ground that is doing all the heavy calculations. And yes, this is a place where we run all the protocols or the control of our constellation. Yeah.
Sounds like we have some pretty big human brains on the ground too, working on these very difficult problems. Listen, Christian, time flies when you're networking in space, but I think we've pretty much run out of time here. So thank you very much for coming on, and thank you everyone for listening. This has been Brian Carney and Cristian La Rocca at Rivada, and watch this space. Stay tuned for more episodes. Thank you.
Thanks. Bye bye.
Bye.